Black holes are among the most intriguing phenomena in space, often portrayed in popular culture as cosmic monsters capable of devouring everything in their path. A prime example of this portrayal is the film Interstellar, where black holes are depicted with a mix of scientific accuracy and creative imagination. So, what exactly is a black hole? At its core, a black hole is a region in space where gravity is so intense that not even light can escape its grasp. This extreme gravity occurs because the black hole's mass is concentrated into an incredibly small space. This leads to the formation of two critical features: the event horizon and the singularity. The event horizon is the boundary surrounding the black hole. It's the point beyond which nothing can escape. The singularity, on the other hand, is the central point where gravity becomes infinitely strong and the curvature of space-time is infinitely warped. Black holes themselves are invisible because they don't emit light, making them detectable only through their interactions with nearby matter and light. To understand black holes better, we need to get into Einstein's theory of relativity. This theory revolutionized our understanding of space and time. Einstein's special theory of relativity, introduced in 1905, tells us that the faster an object moves, the slower time passes for it relative to a stationary observer. Imagine traveling in a spaceship at near light speed. Time would appear to slow down for you compared to someone who stays on Earth. This effect is known as time dilation. Einstein's general theory of relativity, published in 1915, extends this idea by describing how gravity affects time and space. According to this theory, the presence of mass warps the fabric of space-time, causing time to slow down in stronger gravitational fields. This warping of space-time is particularly pronounced near black holes. The closer you are to a black hole, the more time slows down compared to someone further away. This phenomenon was dramatically depicted in Interstellar, where a planet close to a black hole experienced 7 years of time for every hour that passed. Black holes are not born from nowhere. They're formed from the remnants of massive stars. Stars, including our Sun, generate energy through nuclear fusion at their cores, which creates an outward pressure that balances the inward pull of gravity. When a star exhausts its nuclear fuel, this balance is disrupted. For stars with masses much greater than our Sun, this imbalance leads to a spectacular explosion known as a supernova. The core of the star then collapses under its own gravity. If the remaining mass is sufficient, it condenses into a black hole. For smaller stars, they end their lives as white dwarfs or neutron stars instead. White dwarfs are remnants of smaller stars that have shed their outer layers and left behind a dense core. Neutron stars, which are more massive than white dwarfs but not quite enough to become black holes, are incredibly dense objects formed from the collapse of more massive stars. The Chandrasekhar limit, established by astrophysicist Subramanian Chandrasekhar, states that if a star's mass exceeds about 1.4 times that of the Sun, it cannot remain a white dwarf and will instead collapse further into a neutron star or a black hole. The process of black hole formation is a dramatic one, with the remnants of a star being compressed into an incredibly small space, creating a region where gravity is so intense that it becomes impossible for anything to escape. This is why black holes are such captivating objects. They challenge our understanding of physics and our perception of the universe. So, what would happen if you fell into a black hole? The answer is not entirely clear, as this is still an area of active research and speculation. You'd encounter the event horizon, where gravity becomes so powerful that escape is impossible. Beyond this point, the intense gravitational forces would stretch and compress anything falling in, a process known as spaghettification. Whether you'd be disintegrated or encounter a mysterious singularity remains one of the greatest questions in modern astrophysics. Black holes come in several types, each formed under different circumstances and varying greatly in size. The most common type is the stellar black hole, which forms from the collapse of massive stars. When a star exhausts its nuclear fuel, it can no longer support itself against its own gravity and implodes, creating a black hole. These stellar black holes typically have masses ranging from a few to several tens of times the mass of our Sun. In contrast, primordial black holes are hypothetical and thought to have formed in the early universe. These are not just small in physical size, but also incredibly dense. Their mass could be equivalent to that of a mountain or even a city, but they would be as tiny as an atom. Although these black holes are still theoretical and have not been observed, they represent an intriguing area of research. Then there are supermassive black holes, which are found at the centers of galaxies, including our own Milky Way. These black holes are truly colossal, with masses ranging from millions to billions of times that of our Sun. For instance, the supermassive black hole at the center of our galaxy is known as Sagittarius A. Scientists believe that every major galaxy harbors a supermassive black hole at its core, playing a crucial role in galactic formation and evolution. Another intriguing category is intermediate black holes. These are theorized to exist somewhere between the sizes of stellar and supermassive black holes. Despite their theoretical status, researchers speculate that these black holes might bridge the gap between their smaller and larger counterparts, though direct evidence for their existence is still lacking. Observing black holes presents unique challenges because they do not emit light themselves. However, we can study the material around them. This material forms an accretion disk, a swirling ring of gas and debris that becomes extremely hot and luminous as it spirals into the black hole. The accretion disk emits intense radiation, allowing us to detect the presence of a black hole indirectly. One of the most groundbreaking achievements in black hole observation came in 2019 with the first ever photograph of a black hole. This image, taken by the Event Horizon Telescope, captured the shadow of a black hole and its glowing accretion disk. The photo shows a bright, ring-like structure around a dark center, with the bright side appearing more luminous. This brightness variation is due to the Doppler beaming effect, where material moving toward us appears brighter than the material moving away. The image also reveals an optical illusion created by the black hole's gravity. Light bending around the black hole can make the accretion disk appear as though it surrounds the black hole in a more three-dimensional way than it actually does. This effect demonstrates the powerful gravitational influence black holes exert on their surroundings. Now, what happens if you were to fall into a black hole? As you approach the event horizon, the boundary beyond which nothing can escape, the experience would be anything but ordinary. The event horizon is the point of no return. Once crossed, not even light can escape the black hole's grip. If you were to cross this boundary, you would encounter extreme gravitational forces. This would lead to a process known as spaghettification, where the difference in gravitational pull between your head and feet would stretch and compress your body into a long, thin shape. Imagine being pulled apart like spaghetti due to the intense tidal forces. Inside the event horizon, the concept of time becomes distorted. To an outside observer, you would seem to slow down and fade away as you approach the horizon, while from your perspective, you might see the universe outside accelerating in time. This bizarre experience raises questions about the nature of time and space. At the center of a black hole lies the singularity, a point where gravity becomes infinitely strong and space-time curvature becomes infinite. Here, our current understanding of physics breaks down, and traditional laws of nature no longer apply. The singularity represents a fundamental limit to our knowledge about black holes. Looking ahead, black holes are not eternal. They can eventually evaporate through a process known as Hawking radiation. This phenomenon, proposed by physicist Stephen Hawking, suggests that black holes emit radiation due to quantum effects near the event horizon. Over incredibly long timescales, this radiation causes the black hole to lose mass and gradually shrink. As a black hole loses mass, it heats up and emits more radiation. When it becomes as small as an asteroid, it emits heat equivalent to that of our sun. In its final moments, a black hole can release energy comparable to billions of nuclear bombs in a dramatic explosion. However, this process is incredibly slow, and the largest black holes might take longer than the current age of the universe to fully evaporate. Well, we can say black holes are not the cosmic vacuum cleaners once thought to be gulping everything in their path. Instead, they're complex objects that challenge our understanding of the universe. They come in various forms, from stellar to supermassive, and each type reveals different aspects of their enigmatic nature. While the exact fate of an object falling into a black hole remains one of the universe's greatest mysteries, ongoing research and observations continue to deepen our understanding of these fascinating cosmic phenomena. Dark matter is one of the most perplexing and fascinating mysteries in modern astrophysics. Despite its elusive nature, the evidence for dark matter's existence is overwhelming. Yet it remains deeply frustrating because we still don't fully understand what it is. Dark matter is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Yet it has stubbornly resisted all attempts to be directly detected or explained by current theories. We do know a few key things about dark matter. It's believed to be cold, meaning it moves slowly compared to the speed of light. It's also collisionless, meaning it doesn't interact with itself or ordinary matter in any significant way beyond gravity. Most intriguingly, dark matter is incredibly abundant, so much so that it's thought to make up about 85% of the total mass of the universe. Understanding what dark matter is made of could provide crucial insights into the dynamics of galaxies and the evolution of the universe as a whole. Given that it's the most common type of particle in the universe, figuring out its nature is one of the most pressing questions in physics today. To grasp the challenge of understanding dark matter, imagine being in a small boat in the middle of the ocean on a dark night. In the distance, you see the faint lights of a shore. These lights tell you that the shore exists, but they don't reveal anything about what that shore is like, whether it's rocky, mountainous, or covered in dense jungle. This is similar to our current understanding of dark matter. The luminous objects we observe in the universe, such as stars and galaxies, give us clues that dark matter is there. However, just as those distant lights don't tell you about the shore, the visible matter in the universe doesn't tell us what dark matter's made of. We know it's out there, influencing everything we see, but its true nature remains hidden. The evidence for dark matter comes from various astronomical observations that cannot be explained by visible matter alone. One of the most compelling pieces of evidence is found in the rotation curves of galaxies. When we observe how stars move within galaxies, their speeds do not decrease as expected with distance from the galactic center. Instead, they remain relatively constant, suggesting the presence of additional unseen mass, dark matter, exerting gravitational force. Other evidence comes from the temperatures of galaxy clusters. These massive structures are too hot to be held together by the gravity of their visible matter alone. Dark matter provides the additional gravitational pull needed to explain their stability. Gravitational lensing, where light from distant objects is bent around massive structures, also reveals dark matter's presence. The bending is stronger than it would be if only visible matter were involved, indicating more mass. Again, dark matter. The large-scale structure of the universe itself, which shows how galaxies are distributed across vast cosmic distances, matches predictions made when dark matter is included in models. Finally, the cosmic microwave background contains patterns that suggest dark matter played a crucial role in the early universe. Together, these pieces of evidence make a compelling case for the existence of dark matter, even though its exact nature is still unknown. While we have strong evidence that dark matter exists, we also know quite a bit about what it isn't. It's not made up of the same kind of matter that makes up stars, planets, or any of the other objects we can see in the universe. These familiar forms of matter are simply not abundant enough to account for all the gravitational effects observed. Nor is dark matter made up of objects like black holes, rocks, or dim stars. Such things would still interact with light in some way, and dark matter does not. For dark matter to explain the observed phenomena, it must be cold, meaning it moves at relatively slow speeds compared to the speed of light. This is crucial because fast-moving particles would not clump together to form the dense structures we see in the universe. Additionally, dark matter must be collisionless, meaning it doesn't interact with itself or other matter through forces like electromagnetism, which is why we don't see it directly. It only interacts through gravity, which is why it's detectable through its influence on visible matter. One of the strongest pieces of evidence for dark matter comes from studying the rotation curves of galaxies. In a galaxy, stars orbit around the center due to gravity. According to Newtonian mechanics, we expect stars closer to the center of the galaxy, where most of the mass is concentrated, to orbit faster. As we move farther out, where there's less visible mass, the orbital speed of the stars should decrease. This would produce a rotation curve that rises steeply near the center and then falls off. However, observations tell a different story. Instead of slowing down, the orbital speed of stars levels off and remains constant, even far from the galactic center. This discrepancy suggests that there's much more mass present than what we can see, an invisible mass that extends far beyond the visible boundaries of the galaxy. This unseen mass is what we refer to as dark matter, and it appears to be spread out in a halo around galaxies, affecting the motion of stars and gas. Further studies have shown that this dark matter isn't just randomly distributed. It forms halos around galaxies with a specific structure. This structure is described by what is known as the Navarro-Frank-White (NFW) profile, named after the astronomers who developed it. The NFW profile gives us a formula that describes how the density of dark matter changes with distance from the center of a galaxy. According to the NFW profile, the density of dark matter is highest at the center of the galaxy and decreases with distance, following a specific mathematical pattern. This profile fits observations of many galaxies and galaxy clusters, suggesting that dark matter behaves in a similar way across the universe. This consistency provides insights into the formation and evolution of galaxies and their dark matter halos. While theoretical models provide a framework for what dark matter might be, finding concrete evidence of its existence requires innovative experimental approaches. Various hypotheses suggest that dark matter could be made of several different types of particles, each with unique properties and detection challenges. One prominent candidate for dark matter is weakly interacting massive particles, WIMPs. These hypothetical particles would interact only very weakly with ordinary matter, making them hard to detect. Scientists have designed numerous experiments to catch WIMPs in the act, including using ultra-cold detectors and sensitive instruments buried deep underground to shield against other types of radiation. Another intriguing candidate is axions, which are very light hypothetical particles predicted by some theories to solve certain problems in particle physics. Axions might interact very weakly with ordinary matter, but they could be detected through their effects on electromagnetic fields or by their potential to convert into photons in strong magnetic fields. Primordial black holes are another possible form of dark matter. These are black holes that could have formed soon after the Big Bang, and their presence would have significant effects on the formation of structures in the early universe. Detecting primordial black holes would involve looking for their gravitational effects or radiation they might emit. Sterile neutrinos are a type of neutrino that doesn't interact via the weak force like regular neutrinos, but could still be part of the dark matter. They're difficult to detect because they interact even less with matter than ordinary neutrinos. To identify these dark matter candidates, scientists use a variety of experimental techniques. One method is gamma ray detection. If dark matter particles can annihilate each other, they might produce gamma rays that can be detected by space-based telescopes. Another approach involves observing the effects on stars and planets. Dark matter particles might cause unusual heating in stars or other celestial objects if they interact in specific ways. Ultra-cold detectors are designed to pick up tiny amounts of heat generated when dark matter particles collide with the detector material. These detectors are often located deep underground to minimize interference from cosmic rays and other sources of noise. Pure xenon or argon detectors are another method where these noble gases are used in highly purified and low background environments. The idea is that dark matter particles might interact with these gases and produce detectable signals, such as flashes of light or tiny electrical charges. Despite these extensive efforts, direct detection of dark matter has so far been elusive. However, the ongoing search is crucial because even negative results help refine theoretical models and focus future experiments. Confirming dark matter's existence is already a significant achievement, though the nature of this dark matter remains unclear. Neutrinos are an example of dark matter particles in the sense that they do not interact with light, but they are not massive enough to account for the total amount of dark matter we observe. Thus, researchers continue to explore different types of particles, such as heavy neutrinos or other exotic particles like WIMPs, to find a better match for the dark matter we know exists. Additionally, understanding dark matter might also shed light on the conditions of the early universe. It's possible that dark matter played a role in events such as baryogenesis, which explains why the universe is dominated by matter rather than antimatter. Investigating these possibilities helps scientists connect dark matter research with broader questions in cosmology and particle physics. Dark matter remains one of the biggest puzzles in science today, posing more questions than answers. Whether dark matter is a single, simple type of particle or a more complex mix of different particles is still an open question. The possibility of new forces or undiscovered theories of gravity also lingers as potential explanations. As it stands, dark matter serves as a framework for understanding many cosmic phenomena, providing a foundation even though the details are still being worked out. The current state of knowledge about dark matter is similar to an unfinished house that's structurally sound but lacking in the final details that would make it complete. Could dark matter provide clues to other cosmic mysteries, such as the nature of gravity or the origins of the universe? Quantum mechanics often feels spooky because it challenges our understanding of reality itself, and this becomes even more intriguing when linked to consciousness. The idea that particles can exist in multiple states simultaneously and affect each other instantly over distances suggests a reality that doesn't conform to classical logic. When we relate this to consciousness, some theories propose that our awareness might somehow be intertwined with these quantum processes. In the 1930s, the renowned physicist Albert Einstein found himself troubled by a strange aspect of quantum mechanics. This was the idea that two particles, no matter how far apart they were in the universe, could instantly affect each other's behavior. He referred to this puzzling phenomenon as spooky action at a distance because it seemed to contradict the well-established law of physics, particularly his own theory of relativity, which states that nothing can travel faster than the speed of light. However, quantum entanglement, as this phenomenon is called, is now widely accepted and experimentally proven. But what if this strange connection between particles is more than just a quirky aspect of quantum mechanics? What if it hints at something much deeper, like a universal consciousness that links everything in the universe? This idea suggests that the connections we see in quantum mechanics might be a reflection of a more profound truth, that all beings and particles are connected through consciousness itself. To grasp the concept of quantum entanglement, we first need to understand a fundamental property of particles known as spin. Despite its name, spin doesn't mean that particles are literally spinning like tops. Instead, it's a type of intrinsic angular momentum, which can be thought of as the particle's built-in rotation. This spin gives particles an orientation in space. When we measure a particle's spin, we can only do so in a specific direction, such as up or down, relative to the chosen direction of measurement. Interestingly, the result of this measurement can only be one of two possible outcomes. Either the particle's spin is aligned with the direction of measurement, which we call spin up, or it's the opposite to that direction, which we call spin down. Here's where it gets intriguing. If the particle's spin is vertical, but we choose to measure it horizontally, there's a 50% chance it'll be spun up and a 50% chance it'll be spun down. And once the measurement is made, the particle's spin is fixed in that direction. This means that the very act of measurement affects the particle's spin, which can be likened to the idea in consciousness studies that observation shapes reality. Now that we understand spin, let's explore how particles become entangled. Entanglement occurs when two particles are linked in such a way that the state of one particle directly influences the state of the other, no matter how far apart they are. For example, if two particles are entangled and we measure the spin of one particle as we spin up in a particular direction, the other particle's spin, when measured in the same direction, will always spin down. This suggests a deep connection between the two particles, as if they are communicating with each other instantaneously. But what if this connection between entangled particles is a physical manifestation of a broader connection that exists between all things? Just as these particles are connected, perhaps all beings are connected through a shared consciousness. This would imply that, at a fundamental level, everything in the universe is interlinked, much like the particles in a quantum system. The concept of spin becomes even more fascinating when we consider that particles do not have a well-defined spin until we measure it. Before measurement, the particle's spin is not determined. It exists in a state of uncertainty, where it could be either spun up or spun down. This challenges the traditional idea of a predefined reality, suggesting instead that reality itself may be undefined until it is observed or experienced. In the context of consciousness, this idea takes on an even deeper meaning. If particles do not have a defined state until observed, could this imply that reality is shaped by consciousness? In other words, just as a particle's spin is determined by measurement, perhaps the world around us is shaped by our conscious awareness. This perspective invites us to consider the possibility that consciousness plays an active role in creating reality, rather than merely perceiving it. Einstein, along with some other physicists, was uncomfortable with the idea that particles could be connected in such a mysterious way without some underlying mechanism. He proposed that perhaps the particles contained hidden variables, or information that predetermined their spin states, even before measurement. This would mean that the particles were not actually communicating faster than light, but simply revealing information that was already there. To test this idea, physicist John Bell developed an experiment that could determine whether particles indeed carried hidden information or if they were truly connected in the mysterious way that quantum mechanics suggested. In Bell's experiment, pairs of entangled particles are sent to two detectors that randomly choose one of three possible directions in which to measure the spin. The key to the experiment lies in comparing the results from the two detectors. If the particles contained hidden information, the results would differ more than 5 out of 9 times. However, the experimental results showed that the spins were different only 50% of the time, suggesting that there were no hidden variables guiding the particles. Instead, it seemed that the particles were truly connected in a way that defies classical explanations. This outcome has profound implications for our understanding of reality and consciousness. If particles do not contain pre-existing information about their spin, it suggests that their states are determined only at the moment of measurement, reinforcing the idea that observation, perhaps consciousness itself, plays a crucial role in shaping reality. This aligns with the notion that reality is not fixed, but fluid and interconnected, just like the consciousness that may underlie all existence. Quantum entanglement is one of the most mysterious and fascinating aspects of quantum mechanics. It suggests that two particles, even if separated by vast distances, are somehow connected so that the state of one instantly influences the state of the other. This has led to various interpretations among scientists and thinkers. One interpretation is that particles might communicate with each other faster than light, sending information instantly across space. However, this idea clashes with Einstein's theory of relativity, which says that nothing can travel faster than light. Another interpretation is that entangled particles are not communicating at all. Instead, they're so deeply connected that the state of one particle automatically determines the state of the other, no matter the distance between them. But what if this connection between particles is more than just a physical phenomenon? Some people believe that it might be evidence of a deeper, universal consciousness, a force that connects everything in the universe. This idea suggests that consciousness itself could be the thread that ties all particles, beings, and even the universe itself. If we consider the possibility that consciousness is a unifying force, quantum entanglement takes on a whole new meaning. The instant connection between entangled particles might be a reflection of this deeper truth that all things in the universe are interconnected through a shared consciousness. This consciousness might be what allows particles to know the state of their entangled partners, no matter how far apart they are. In this view, consciousness is not limited to individual beings, but is a fundamental part of the fabric of the universe. Just as quantum entanglement shows that particles are not separate, but part of a connected whole, consciousness might be the underlying force that connects all of existence. This idea opens up the possibility that we, too, are connected to everything around us through this universal consciousness. The universe seems less like a big machine and more like a big thought. This idea suggests that being aware isn't just limited to our brains or bodies. It extends beyond space and time into a vast field of awareness. Whether we recognize or understand this doesn't change the reality. Studies, like those conducted at Princeton, show that human consciousness can influence a random number generator, or RNG, that spins zeros and ones randomly. When people focus their awareness on it, the RNG's output shifts, similar to how quantum processes work, where outcomes aren't strictly predictable. This suggests that consciousness isn't just an illusion or something confined to the brain. It can actually affect probabilities. At the deepest level, in quantum mechanics, mind and matter aren't separate. They're different aspects of one whole, constantly interacting. Understanding the connection between physics and consciousness is important. Photons, people, and awareness are all linked and not limited by space and time. Another compelling experiment was conducted by Dr. Masaru Emoto, a Japanese scientist who explored the impact of human intention on water. He exposed water samples to different thoughts, words, and music, and then froze them. The resulting ice crystals were photographed, revealing that positive intentions produced well-formed, beautiful crystals, while negative intentions led to distorted, chaotic structures. So the human consciousness can affect the physical world even at the molecular level. While quantum entanglement does not allow for faster-than-light communication, it does hint at a much deeper connection between particles and possibly between all things in the universe. The results of quantum experiments show that the connection between entangled particles is real, but it doesn't involve sending information faster than light. Instead, it suggests that these particles are linked in a way that transcends physical space and time. This connection is, indeed, spooky, as Einstein put it, but it also invites us to think about the possibility of a deeper, more profound connection through consciousness. Even though we can't use quantum entanglement to send messages instantly across the universe, it does show us that the universe is more interconnected than we might have imagined. Quantum mechanics challenges our understanding of reality in many ways, and quantum entanglement is one of the most striking examples. It forces us to question the nature of reality and question the possibility that consciousness plays a key role in shaping the world around us. Wormholes capture the imagination as intriguing shortcuts through the cosmos, promising solutions for space travel, time travel, and even journeys to alternate universes. Their allure is not just in their science fiction appeal, but in the real scientific theories and predictions that have shaped our understanding of these fascinating structures over time. The idea of wormholes began with Ludwig Flamm in 1916, when physicists were grappling with the complexities of Einstein's field equations in general relativity. Flamm was exploring solutions and proposed the existence of white holes, which would be the opposite of black holes. In his theory, matter falling into a black hole could be expelled through a white hole, connected by a kind of space-time conduit. This conduit, or tunnel, would bridge 2 points in space-time, potentially even in different universes. Though his ideas were speculative and not widely recognized at the time, they laid the groundwork for future developments. The concept gained traction when Albert Einstein and Nathan Rosen revisited it in 1935. Their paper extended Flamm's idea, introducing what we now call Einstein-Rosen bridges. These bridges, which are a type of wormhole, were initially proposed as shortcuts between distant points in space-time within the same universe. This conceptual leap highlighted the potential for wormholes to act as cosmic shortcuts, allowing for rapid travel between distant locations. To visualize how a wormhole might work, think of a flat sheet of paper representing the universe. If you draw a point at each end of the paper and then fold the paper so that the 2 points touch, you've created a shortcut between them. If you then poke a pencil through the folded paper, that pencil represents the wormhole, a direct connection between 2 points that bypasses the distance of the flat paper. This analogy helps illustrate the basic idea. A wormhole is a tunnel-like structure that provides a shortcut through space-time. However, while the mathematics behind wormholes suggests they could exist, their practical discovery and utilization are far from guaranteed. Theoretical models show that wormholes might be possible, but they also come with significant challenges. One major issue is their stability. Theoretical work indicates that if a wormhole were to form, it might be incredibly unstable, collapsing almost instantly due to gravitational forces. This collapse would happen so quickly that not even light could pass through, making them practically unusable for any form of travel. The idea of wormholes remains compelling largely because they offer a solution to some of the most pressing problems in physics. They provide a theoretical means of overcoming the vast distances between stars and even offer tantalizing possibilities for time travel. Yet, despite the elegant solutions wormholes offer, the reality of their existence and stability is still uncertain. The fascination with wormholes persists because they sit at the intersection of profound theoretical physics and imaginative science fiction, pushing the boundaries of what we know about the universe and our place within it. Reversible wormholes, the kind of wormholes that could theoretically allow matter to pass through, involve a fascinating mix of theoretical concepts and daunting challenges. At the heart of the discussion is the need for exotic matter, a hypothetical substance with properties that defy our conventional understanding of physics. Exotic matter is proposed to possess negative energy density, an essential feature for keeping a wormhole open. In simple terms, this means it would exert repulsive gravitational forces, counteracting the intense pressure that would otherwise cause the wormhole to collapse. Negative mass, a form of exotic matter, would behave counterintuitively to positive mass. Instead of being attracted by gravity, it would be repelled, allowing the wormhole to remain stable. This counteracting force is critical, as without it, the wormhole would quickly pinch off, rendering it useless for practical purposes. However, the search for and use of exotic matter presents its own set of problems. Negative mass, if it exists, is currently undetectable with our present technology, and no examples of exotic matter have been observed. Even if such matter could be found, integrating it into a wormhole and maintaining its stability would be extraordinarily complex. The introduction of ordinary matter, such as a person or spacecraft, could disrupt the delicate balance required to keep the wormhole open, potentially leading to its collapse. Another significant challenge is Hawking radiation, a theoretical prediction that black holes emit radiation due to quantum effects near their event horizons. Similar effects are thought to apply to wormholes. This radiation could cause the wormhole to shrink and close, limiting its usefulness. The presence of Hawking radiation would impose a strict time limit on how long a wormhole could remain open and stable, complicating any plans for using them for space travel or communication. Alternative theories offer intriguing possibilities for wormholes, though they also come with their own complexities. The E=ER conjecture, proposed by Leonard Susskind and Juan Maldacena, suggests that quantum entangled particles are connected by wormholes. This idea attempts to bridge the gap between general relativity and quantum mechanics, offering a potential avenue for unifying these two fundamental theories. If correct, this conjecture could offer a new perspective on how wormholes function at a quantum level, though it remains a theoretical proposal rather than a practical solution. String theory provides another intriguing framework. According to some interpretations of string theory, wormholes could have been created during the early moments of the universe. These primordial wormholes might have been tiny, on the Planck scale, but cosmic inflation could have expanded them to a macroscopic size. If such wormholes exist and can be stabilized, they could offer a means of creating shortcuts across the universe. When it comes to practical uses, wormholes could revolutionize space travel. If we could create a network of wormholes, it might be possible to establish a wormhole commuter hub, allowing for rapid travel across vast distances in space. This would transform our approach to exploring and inhabiting other parts of the galaxy. Additionally, wormholes might enable time travel, a concept that has fascinated both scientists and science fiction enthusiasts. By accelerating one end of a wormhole to near the speed of light, time dilation could create a scenario where traveling through the wormhole allows movement backward or forward in time. However, practical time travel via wormholes faces significant limitations and paradoxes. The process of time travel would not allow for free movement to any time or place. Instead, you could only travel to moments before or after the creation of the wormhole itself. For instance, you couldn't travel back to prevent historical events like the assassination of historical figures. You'd be limited to arriving at times when the wormhole was operational and at the location where the other end of the wormhole was positioned. The future of wormholes remains a tantalizing frontier in both theoretical and experimental physics. Recent developments have sparked significant excitement and speculation, particularly around advancements in technology and understanding that could bring us closer to unraveling the mysteries of these cosmic shortcuts. In 2022, news stories emerged claiming that scientists had created the first ever wormhole in a lab. However, these reports were met with skepticism and confusion. The excitement stemmed from a paper published by a team led by Jane Ferris, which explored the ER equals EPR conjecture using quantum computers. The conjecture, proposed by physicists Leonard Susskind and Juan Maldacena, suggests that wormholes, ER, might be linked to quantum entanglement, EPR. While the research used simulations to test these ideas, the actual creation of wormholes remained speculative. The media's sensationalism around the paper led to misinterpretations, suggesting breakthroughs that were not yet realized. Despite the sensational headlines, the work done with quantum computers represents a meaningful step forward in our understanding. By testing theoretical models like the ER equals EPR conjecture, researchers are inching closer to reconciling general relativity with quantum mechanics. Such advances could eventually lead to real discoveries about wormholes, though we're still far from practical applications. Theoretical physics continues to explore new possibilities, and one intriguing theory suggests that wormholes might be optical illusions. This idea relies on the concept that wormholes, if they exist, might require additional spatial dimensions. One analogy often used is the Klein bottle, a four-dimensional mathematical construct that appears to have a single side and no boundaries in its higher dimensional form. In 3 dimensions, a Klein bottle looks like it has an opening, but this is merely a shadow of its true form. Similarly, the entrances to wormholes might be illusions created by higher dimensional spaces, making it seem as though there's a tunnel, when in reality, there might not be one. As we continue to investigate these possibilities, the future of wormholes remains a blend of hope and uncertainty. While we await further discoveries, the excitement about potential breakthroughs in space and time travel fuels our imagination. Each advancement in theoretical and experimental physics brings us one step closer to understanding whether wormholes are more than just theoretical constructs. For now, the journey toward uncovering the true nature of wormholes is ongoing, keeping us on the edge of our seats as we explore the limits of our universe. The Big Bang Theory is the cornerstone of modern cosmology, encapsulated in the lambda CDM model. This theory proposes that the universe began as an incredibly hot and dense point around 13.8 billion years ago and has been expanding ever since. The lambda CDM model provides a comprehensive framework for understanding the universe's large-scale structure and evolution. According to this model, the universe's expansion from an initial state of extreme density and temperature marks the beginning of all space, time and matter. Despite its success in explaining many aspects of the universe, there are significant gaps in our understanding. The events that occurred before the Big Bang, often referred to as the time before time, are still not well understood. Theories suggest that the conditions and mechanisms that led to the Big Bang are beyond our current observational reach, leaving a fascinating yet unresolved mystery at the heart of cosmology. The term Big Bang might evoke the image of a colossal explosion, but this is somewhat misleading. The Big Bang was not an explosion in space, but rather an expansion of space itself. Imagine a balloon being inflated. It's not the balloon exploding, but the balloon's surface stretching and expanding. Similarly, the Big Bang describes the expansion of space, causing galaxies to move away from each other as the universe grows. Animations that depict the Big Bang from an outside perspective can be confusing, as they suggest a central explosion in pre-existing space. In reality, every point in space was part of the expanding universe, so there was no outside to witness the event. The observable consequences of the Big Bang include a dramatic decrease in the universe's density and temperature. As the universe expanded, it cooled down, allowing the formation of subatomic particles and eventually the atoms that make up the stars and galaxies we see today. Before the Big Bang, the universe experienced a phase known as inflation. During this epoch, the universe expanded at an extraordinarily rapid rate, far exceeding the speed of light. This period of exponential growth means that within a fraction of a second, the universe expanded from a size smaller than an atom to something much larger than the observable universe. This rapid expansion, called inflation, smoothed out the universe and set the stage for the Big Bang. As inflation ended, the energy driving this expansion was released into space. This energy heated up the universe and resulted in the formation of fundamental particles. These particles eventually combined to form atoms, stars, galaxies, and other cosmic structures. This transformative process, marking the end of inflation, is what we refer to as the Big Bang. It's the point where the universe as we know it began to emerge from an initially hot and dense state. The Big Bang theory is supported by several key observations. In 1929, Edwin Hubble discovered that galaxies are moving away from us, leading to the formulation of Hubble's law. This observation provided strong evidence for the expansion of the universe, a cornerstone of the Big Bang theory. Another significant piece of evidence is the discovery of cosmic microwave background, CMB radiation. In 1964, Arno Penzias and Robert Wilson accidentally detected this faint glow of radiation, which is a remnant from the early universe. The CMB is often described as the afterglow of the Big Bang and provides a snapshot of the universe approximately 380,000 years after the event. This radiation fills the universe and offers a detailed picture of the early conditions, further validating the Big Bang theory. Einstein's theory of general relativity revolutionized our understanding of the universe by merging space and time into a single intertwined fabric known as space-time. According to this theory, the gravitational force we experience is actually the result of the curvature of space-time caused by massive objects. This elegant model describes how objects move and interact within this four-dimensional continuum, providing a framework for understanding phenomena like black holes and gravitational waves. However, this merging of space and time poses challenges when we attempt to conceptualize the moments before the Big Bang. General relativity breaks down at the singularity, where the density and temperature become infinitely large. Trying to describe what happened before the Big Bang is like asking what's north of the North Pole, a question that doesn't fit within our current understanding of space and time. In essence, the concept of before might be meaningless if time itself began with the Big Bang. To address the mysteries surrounding the Big Bang and the universe's origins, physicists have proposed several speculative theories. These theories extend beyond the well-established Big Bang model and delve into more abstract and novel ideas. It's important to note that while these theories are intriguing, they remain speculative and are active areas of research rather than established science. One such speculative theory is the cyclic universe, or bouncing universe model. This theory proposes that the universe undergoes an endless series of expansions and contractions. According to this model, our universe is just one of many cycles of a cosmic bouncing process. After each expansion, the universe eventually contracts, culminating in a big crunch that leads to another Big Bang, starting the cycle anew. The cyclic model implies that time could be infinite, as each cycle represents a new beginning after an end. However, current observations reveal that the universe's expansion is accelerating due to a mysterious force known as dark energy. This acceleration challenges the idea of a cyclical model because it suggests that the universe might continue to expand indefinitely rather than eventually contracting. Additionally, this theory intersects with string theory, which posits the existence of extra dimensions and could potentially provide a framework for understanding these cyclic processes. Another speculative idea is the multiverse concept, which suggests that our universe might be just one of many, potentially an infinite number of universes. This idea is closely related to the eternal inflation theory. According to this theory, the inflationary phase of the universe's expansion didn't end everywhere at once. Instead, it continues in some regions, creating bubble universes within a larger, ever-inflating space. In this scenario, each bubble universe, including ours, would have its own set of physical laws and constants. The process of eternal inflation means that new universes are constantly being formed, resulting in a vast multiverse where every possible combination of natural laws exist. The implications of this are profound, suggesting that our universe is just one bubble in a much larger cosmic foam. The idea of a multiverse provides a framework for addressing the fine-tuning of our universe. If there are countless universes with varying properties, it's not surprising that we find ourselves in a universe that supports life. It would be inevitable among all the possibilities. Another intriguing idea is that our universe could have merged from nothing, a concept that seems paradoxical at first, but gains credibility through quantum mechanics. In the strange world of quantum physics, the idea of nothing is not as empty as we might imagine. According to the Heisenberg uncertainty principle, even in a perfect vacuum, what we might call nothing, there are still fluctuations in energy. These quantum fluctuations mean that particles can spontaneously appear and disappear in extremely short time frames. This principle suggests that, under the right conditions, a universe could spontaneously form from these quantum fluctuations. Essentially, the energy required to create a universe like ours could arise out of these fleeting quantum events, leading to a sudden Big Bang. In 2014, a scientific paper provided a mathematical framework supporting this idea, showing that it's theoretically possible for a universe to emerge from a state of quantum nothingness. This concept challenges our traditional understanding of cause and effect, suggesting that our universe might not require a cause in the conventional sense. Instead, it could be the result of random quantum fluctuations, an idea that aligns with the unpredictable nature of quantum mechanics. Despite the elegance and appeal of these theories, they all confront the same fundamental challenge: the limitations of our current knowledge. At the singularity before the Big Bang, the density and temperature of the universe become infinite, causing the laws of physics as we know them, particularly general relativity, to break down. This is where our understanding hits a wall, and why developing new theories, like quantum gravity, is so crucial. Quantum gravity, which aims to reconcile general relativity with quantum mechanics, could provide the tools needed to understand what happened before the Big Bang, or even if the concept of before is meaningful. When we talk about the universe, we're usually referring to the observable universe, the region of space from which light has had time to reach us since the Big Bang. This observable universe spans approximately 94 billion light-years across. While this might seem vast, it's likely just a small part of a much larger, possibly infinite universe. The limits of what we can observe are set by the speed of light and the age of the universe, not by the actual extent of the universe itself. The universe is believed to extend far beyond what we can observe, and our current measurements suggest that it might be infinite. However, we remain uncertain about its exact size and shape. The observable universe might just be a tiny bubble in a much larger, possibly infinite expanse, and beyond it could lie regions of space that are vastly different from our own. Looking ahead, the universe's future seems to be one of endless expansion. Observations indicate that this expansion is accelerating, driven by a mysterious force known as dark energy. If this acceleration continues, the universe will keep growing indefinitely, with galaxies moving further apart until they become isolated in an ever-expanding void. Unless new physics emerge to change this trajectory, the universe's future is one of perpetual expansion. While the Big Bang Theory and cosmic inflation offer a robust framework for understanding the universe's beginnings, they also leave us with profound questions. What came before the Big Bang? What lies beyond our observable universe? Theories like cyclic universe, the multiverse, and the universe from nothing push the boundaries of our understanding, but also highlight the limits of current science. As physicists continue their quest to unify general relativity with quantum mechanics, we may one day find answers to these deep and fundamental questions. Until then, the mystery of the universe's origins remains one of the most exciting frontiers in science. Don't forget to subscribe to the channel.